So in the early universe, the universe didn't know how to keep time. You see, it just it lost track of how fast things were going. You see, and if you take that seriously, you can imagine going to before it.
In 1870, San Francisco presented a challenge for railroad travelers headed to Washington State. With no standardized time, adjusting watches over 200 times was necessary to match the diverse local times of each town. The absence of a universal time system became significant with the advent of railroad travel. On November 18, 1883, railroads introduced uniform time at stations to address confusion, leading to the global adoption of standardized timekeeping. Representatives met in Washington, D.C. in 1884 and divided Earth into 24 time zones. World Standard Time divides our timekeeping into tidy, uniform packages, but the exact nature of time remains a mystery. What if I told you that time has no beginning and we might be living in the past? This is what Roger Penrose's conformal cyclic cosmology suggests. So, does the past still exist? Let's find out.
Now, for a long time, you see, if anybody had asked me what happened before the Big Bang, I would have given the conventional answer, which is the Big Bang was this singular state when all our equations go haywire and time and space, doesn't make any sense. Even the question before doesn't mean anything, you see. So that's the conventional answer. You say, now have changed my mind. I'm not sure it's fair to say I've changed my mind, but I have another idea which I'm pursuing, which I think has a reasonable chance of being right. And this depends upon how you characterize the initial state of the universe. So what I'm saying is that the gravity was special. Everything else seems to have been as random as it could be. Now, can you characterize that in some geometrical way?
Roger Penrose's conformal cyclic cosmology has emerged as a thought-provoking and innovative hypothesis that challenges traditional understanding of time and the origin of the universe. To understand Penrose's stance on the existence of the past and the absence of the beginning of time, it's essential to understand the motivations behind conformal cyclic cosmology. Penrose is a renowned mathematical physicist who seeks to reconcile the fundamental concepts of general relativity and quantum mechanics while addressing the mysteries of the Big Bang singularity. Penrose's journey begins with his dissatisfaction with the singularities predicted by general relativity. Singularities represent points where gravitational forces become infinitely strong and where our current understanding of physics breaks down. The Big Bang singularity, in particular, raises questions about the origin of the universe and the nature of time before this cosmic event. Penrose's solution to these challenges is conformal cyclic cosmology, a theory that imagines a cyclical universe with no true beginning or end. The conformal aspect of conformal cyclic cosmology involves a transformation that expands the concept of infinity and introduces the idea of conformal infinity. Instead of a singular starting point, Penrose proposes a cyclic succession of universes, each connected to the other through conformal transformations. At the heart of conformal cyclic cosmology lies the framework of conformal geometry, which is a mathematical discipline that preserves angles while allowing for the transformation of distances.
A universe of angels and devils, and they're all within this circular boundary. And at the edge, you see, that's infinity. And the whole universe is squashed into this disk. Now, if you forget about the size of those angels and devils and just worry about shapes, then doesn't matter how big they are. The little ones at the edge are the same sort of shape as the ones in the middle. But if you are prepared to stretch and squash in a uniform way, okay, that you could stretch that boundary out to infinity, or you could squash it back to this finite boundary. Now, there is a universe. I mean, the universe in this picture stops at the edge, that's infinity. But you could imagine extending it to the other side and preserving this kind of geometry. It's called conformal geometry. That's a mathematical term, which means that, okay, you know about shapes, small shapes, but you don't know about sizes. So small and big count as the same, but different angles count as different, or different small shapes count as different.
Penrose uses the power of conformal geometry to explain the vast expanse of the cosmos by employing transformations that connect different epochs seamlessly. To truly understand conformal cyclic cosmology's mathematical underpinnings, it's essential to delve into conformal geometry. Conformal transformations, which maintain the shape of objects but not necessarily their sizes, offer a unique lens through which the universe's evolution can be understood. In conformal cyclic cosmology, these transformations act as the threads stitching together the cosmic web. The concept of conformal infinity, introduced by Penrose, extends the usual mathematical infinity into a realm where the end of one universe smoothly transitions into the beginning of the next. This departure from a singular starting point challenges traditional cosmological models and paves the way for an infinite yet interconnected cosmic landscape. The visualization of conformal cyclic cosmology's cosmic cycles is facilitated by Penrose's diagrams, which is a powerful tool that distills the complex geometry of spacetime into a comprehensible two-dimensional representation. These diagrams are similar cosmic blueprints and provide a visual narrative of the universe's evolution across different eons. Penrose diagrams are instrumental in understanding the cyclic nature of conformal cyclic cosmology and illustrate how each cosmic cycle undergoes phases of expansion, contraction, and renewal. By mapping conformally transformed spacetime onto a two-dimensional plane, these diagrams unveil the connections between seemingly distinct epochs. A foundation of conformal cyclic cosmology is its endeavor to confront the challenges posed by singularities, particularly those associated with the inception of the universe. Singularities, points where gravitational forces become infinitely strong, have long perplexed physicists. Penrose's departure from these singularities takes a quantum leap, intertwining quantum mechanics with general relativity within the framework of conformal geometry. In conformal cyclic cosmology, singularities transform from mysterious points of infinite density to regions imbued with quantum uncertainty. This quantum perspective redefines our understanding of cosmic origins and introduces a level of granularity at the quantum level that was previously absent in cosmological theories. The marriage of quantum mechanics and general relativity within conformal cyclic cosmology holds the promise of uncovering the mysteries of the universe's earliest moments. Within the quantum gravitational landscape of conformal cyclic cosmology, conformal fluctuations emerge as agents of cosmic renewal. These fluctuations are rooted in the uncertainties of quantum mechanics and act as the catalysts for transitioning between cosmic eons. As the universe undergoes the phases of expansion and contraction, conformal fluctuations introduce an element of unpredictability and give rise to the cosmic cycles. Quantum conformal fluctuations provide a bridge between the macroscopic and the quantum realms and offer a mechanism through which the universe perpetually renews itself. The cyclical nature of conformal cyclic cosmology is intimately tied to these quantum fluctuations and adds a layer of complexity and dynamism to the cosmic narrative. This quantum lens not only reinterprets the nature of singularities, but also reshapes our understanding of the universe's evolution. As conformal cyclic cosmology presents a novel perspective on the cyclical nature of the universe, researchers are compelled to seek observational signatures that could validate or challenge this groundbreaking hypothesis. One such avenue of exploration lies in the cosmic microwave background, or CMB, the faint radiation permeating the cosmos, considered a relic of the early universe. Penrose's conformal cyclic cosmology predicts subtle imprints left by previous cosmic cycles within the CMB. Investigating these traces requires an analysis of the CMB's temperature and polarization patterns, searching for anomalies that align with the expectations set forth by conformal cyclic cosmology. In the era of gravitational wave astronomy, conformal cyclic cosmology introduces a compelling avenue for exploration. Gravitational waves, ripples in spacetime resulting from the acceleration of massive objects, offer a unique lens through which researchers can probe the fabric of the cosmos. In conformal cyclic cosmology, these gravitational waves carry the potential to reveal the subtle ripples of conformal transformations between cosmic cycles. Detecting gravitational waves associated with conformal transformations becomes a frontier in observational cosmology. The challenge lies in distinguishing these cosmic signatures from the myriad sources of gravitational waves present in the universe. Researchers tried to develop sophisticated detectors and analytical techniques capable of teasing out the distinctive signals indicative of Penrose's conformal cyclic cosmology. Roger Penrose's arguments in favor of conformal cyclic cosmology present a paradigm shift in our understanding of the universe's temporal structure. At the core of Penrose's arguments lies a fundamental inquiry into the nature of time itself. Traditional cosmological models often presuppose a singular beginning by the Big Bang and a linear progression from past to present to future. Penrose challenges this linear paradigm by proposing an eternal, cyclical view of time. Penrose's argumentation challenges the prevailing idea of time as a linear progression with a fixed beginning. Within conformal cyclic cosmology, time takes on a cyclical nature, with each eon representing a cosmic cycle of expansion, contraction, and renewal. This cyclical view not only reshapes our understanding of time, but also introduces the idea that the past is not a distant memory, but an enduring reality. The cyclic nature of conformal cyclic cosmology implies an eternal process of cosmic renewal and evolution. Each eon witnesses the universe undergoing phases of expansion, contraction, and reformation. This perpetual cycle eliminates the need for a definitive starting point and challenges the traditional model of cosmic creation. Penrose's argumentation suggests that the universe, rather than having a singular beginning, undergoes an unending sequence of cosmic iterations. This eternal renewal introduces a sense of continuity and interconnectedness across cosmic cycles, and presents a cosmological framework where the past is not merely a historical record, but an active participant in shaping the present and future. Critics may question the philosophical implications of Penrose's timeless universe, and argue that a cyclical view of time challenges our intuitions about existence and the nature of reality. Penrose, however, suggests that our intuitions may be shaped by a linear perspective on time derived from our everyday experiences. Another potential critique centers on the integration of quantum mechanics and general relativity within conformal cyclic cosmology. Critics may question the feasibility of harmonizing these two foundational pillars of modern physics within a conformal cyclic framework. Penrose, however, asserts that the conformal geometry provides the necessary mathematical scaffolding for this integration. The marriage of quantum mechanics and general relativity, while challenging, holds the promise of resolving long-standing issues associated with singularities. Penrose's commitment to mathematical precision shows his confidence in the viability of this integration. The empirical validation of conformal cyclic cosmology poses a significant challenge. Critics may argue that the cyclical nature of the universe, while conceptually interesting, lacks empirical evidence. Penrose, cognizant of this challenge, points to potential observational tests that could substantiate or challenge conformal cyclic cosmology. The investigation of the cosmic microwave background and the detection of gravitational waves provides avenues for empirical validation. Researchers are tasked with developing sophisticated observational techniques capable of discerning subtle signatures indicative of conformal cyclic cosmology. Roger Penrose's conformal cyclic cosmology not only challenges conventional views on the structure of the universe, but also carries profound scientific and philosophical implications. Conformal cyclic cosmology prompts a reconsideration of the traditional Big Bang that suggests a singular beginning of the universe. Penrose's cyclic model suggests that the universe's evolution is not confined to a singular explosive event, but unfolds through an eternal series of cycles. This departure challenges the prevailing narrative that opens avenues for reevaluating our understanding of cosmic origins. As scientific thought evolves, the cyclical nature proposed by conformal cyclic cosmology may become a catalyst for exploring alternative models that better align with observational data. The concept of a multiverse, where multiple universes exist alongside our own, has gained traction in cosmological discussions. Conformal cyclic cosmology's cyclic nature introduces a different perspective on the multiverse hypothesis. Rather than multiple universes coexisting simultaneously, conformal cyclic cosmology suggests an ensemble of universes succeeding each other in a cyclic fashion. This raises questions about the compatibility of conformal cyclic cosmology with other cosmological theories, such as cosmic inflation, which suggests an exponential expansion of the universe in its early moments. Researchers are faced with the challenge of reconciling or differentiating conformal cyclic cosmology from these alternative models and exploring whether a cyclic framework aligns with or challenges the paradigm of a multiverse. Dark energy and dark matter remain mysterious components of the universe and constitute the majority of its mass energy content. Conformal cyclic cosmology introduces a different lens through which to view these cosmic mysteries within the cyclic cosmology. Understanding how dark energy and dark matter behave across cosmic cycles becomes a pertinent question. Do these elusive components exhibit consistent behavior across eons, or does conformal cyclic cosmology suggest variations in their influence over the course of the universe's evolution? Exploring the implications of conformal cyclic cosmology on our understanding of dark energy and dark matter is another interesting topic. The timeless past proposed by conformal cyclic cosmology has profound philosophical implications, as it challenges conventional ideas of time as a mutable, linear entity. If the past endures, it becomes an immutable backdrop against which the present unfolds. The philosophical shift prompts contemplation on the nature of reality and the dynamic interplay between past, present, and future. Penrose's timeless perspective challenges philosophers to rethink established frameworks for understanding the nature of time and existence. The very fabric of reality, as perceived through the lens of conformal cyclic cosmology, invites a deeper exploration of the philosophical foundations that underpin our understanding of the cosmos. The implications of conformal cyclic cosmology also extend to consciousness and the human experience. If the past persists, it raises intriguing questions about the nature of memory, perception, and the subjective experience of time. How does a timeless past influence our understanding of personal histories and the narratives that shape individual consciousness? The bold propositions of conformal cyclic cosmology do not escape criticism. One of the primary critiques of conformal cyclic cosmology, as we've discussed, centers on the empirical challenges associated with testing a cyclic model of the universe. While conformal cyclic cosmology introduces potential observational signatures within the cosmic microwave background and gravitational waves, the subtle nature of these signals poses a considerable challenge for detection. The integration of quantum mechanics and general relativity within conformal cyclic cosmology has also sparked debates about the theoretical coherence of the model. Critics raise questions about the complexities of merging these two foundational pillars of physics, particularly in the context of singularities. While Penrose's quantum resolution to singularities introduces a novel perspective, some researchers suggest that further refinement and development are necessary to ensure the theoretical consistency of conformal cyclic cosmology. The relationship between quantum mechanics and general relativity within the conformal framework prompts discussions about the model's robustness in addressing the fundamental questions it sets out to answer. Occam's razor, the principle of favoring simpler explanations when multiple hypotheses are available, becomes an important point in the critique of conformal cyclic cosmology. Skeptics argue that the cyclic model introduces a level of complexity that may not be warranted, especially when simpler models, such as the standard cosmological model with a singular beginning, exist. The challenge lies in balancing the elegance of a theory with its explanatory power. Critics suggest that conformal cyclic cosmology, with its conformal transformations, multiple eons, and mathematical structure, may introduce unnecessary complexities that could be perceived as contrived. An alternative perspective within cosmology is the theory of eternal inflation and the multiverse hypothesis. Proponents of eternal inflation suggest that the universe undergoes continuous inflationary phases and gives rise to an ever-expanding multiverse with multiple causally disconnected regions. Comparisons between conformal cyclic cosmology and eternal inflation raise questions about the nature of cyclic and simultaneous multiverses. While conformal cyclic cosmology proposes an ensemble of universes succeeding each other in a cyclical fashion, eternal inflation suggests a multitude of parallel universes coexisting simultaneously. The block universe theory, rooted in the philosophy of four-dimensionalism, challenges conventional views of time as a linear progression. According to this perspective, past, present, and future coexist as permanent elements of a four-dimensional space-time block. In contrast to conformal cyclic cosmology's cyclical view of time, The block universe theory introduces a timeless paradigm where all moments in time are equally real. This alternative perspective prompts reflection on the nature of temporal experience and the implications of a universe where the entirety of its temporal tapestry exists as an unchanging entity. The quest for a theory of quantum gravity and the unification of fundamental forces is a central theme in theoretical physics. All this research focuses on refining our understanding of the quantum nature of space-time and developing theories that reconcile quantum mechanics and gravity. In conformal cyclic cosmology, the integration of quantum mechanics and general relativity is an active area of exploration. Researchers seek to refine the mathematical consistency of conformal cyclic cosmology within the broader framework of quantum gravity in order to contribute to the dialogue about the unification of fundamental forces and the nature of singularities. The search for observational evidence supporting or challenging conformal cyclic cosmology continues with an emphasis on cosmic archaeology. Researchers aim to uncover subtle imprints within the cosmic microwave background that may serve as signatures of conformal cyclic cosmology. The exploration of gravitational waves and their potential role in validating conformal cyclic cosmology is a topic of research. Advanced observational technologies, including next-generation telescopes and detectors, play a crucial role in uncovering the cosmic secrets embedded within the fabric of space-time. Advocates for conformal cyclic cosmology argue that complexity is not necessarily a drawback, but a virtue that deepens our understanding of the universe. The mathematical structure, conformal transformations, and cyclical nature of conformal cyclic cosmology provide a framework that addresses long-standing issues in cosmology, such as the nature of singularities and the beginning of the universe. Complexity from this perspective is an essential aspect of theories that aim to uncover the mysteries of the cosmos. Conformal cyclic cosmology's departure from simplicity is seen as a necessary step toward a more comprehensive cosmological framework that accommodates the complexities inherent in the fabric of the universe. Critics of conformal cyclic cosmology, on the other hand, emphasize the guiding principle of Occam's razor, favoring simplicity in theoretical explanations. From this perspective, simpler models that adhere to a singular beginning of the universe, such as the standard cosmological model, may have an edge in terms of elegance and explanatory power. The debate between complexity and simplicity reflects the broader philosophical considerations that shape cosmological theories. As researchers grapple with the complexities of conformal cyclic cosmology and its alternatives, the balance between complexity and simplicity becomes a defining aspect of the discourse surrounding the nature of the cosmos. The integration of quantum mechanics and gravity remains a central challenge in theoretical physics. Future directions in cosmological inquiry involve advancing our understanding of quantum gravity and refining theories that unify the fundamental forces of the universe. Research efforts focus on explaining the quantum nature of space-time, developing consistent mathematical frameworks, and exploring novel avenues for unifying quantum mechanics and general relativity. As progress takes place in this foundational area, the implications for cosmological models, including conformal cyclic cosmology, continue to shape the path of theoretical physics. The future of cosmological inquiry is linked to advancements in observational technologies. The development of more sensitive telescopes, detectors, and interferometers enhances our capacity to probe the cosmos at unprecedented levels of precision. Continuous advancements pave the way for cosmic archaeology, where researchers seek subtle imprints within the CMB and gravitational waves that may validate or challenge conformal cyclic cosmology. The collaboration between theoretical frameworks and observational technologies remains essential for pushing the boundaries of our cosmic understanding. Thanks for watching this video. Let us know your thoughts in the comment section below, and please stay tuned for more content.